So once I had finished putting the methanol into the beaker, Will was performing the calculation for how much the potassium hydroxide needed to be added to the methanol. That was the 0.575 ounces. So once he got that done, he used a scale with a smaller beaker, zeroed it out, used a scrupula to place the potassium hydroxide into the beaker. Once he was able to calculate all that out, he handed it to me, and I started the mixing process. We added approximately 0.115 ounces of potassium hydroxide to the methanol roughly every 2 minutes. The reason why 2 minutes is because that was the time that it roughly took for the potassium hydroxide to mix into the methanol. And we used the magnetic stirrer for that purpose. We would vary the revolutions per minute of the small little mixing stirrer inside the beaker, depending on whether we saw the potassium hydroxide was starting to clump together or whatnot. Next slide. So what we did also was we used a thermometer. We first measured the temperature of the methanol prior, just so that we can get our base average. And that was a temperature of 66 degrees Fahrenheit. And what we would continue to do is that as we were adding the potassium hydroxide, we would take temperature measurements to see if there was a temperature increase. And there actually was a temperature increase. The maximum temperature that we obtained for the solution was 98 degrees Fahrenheit. So, Will is going to come up and actually explain the data that we obtained when we mixed the potassium hydroxide into the methanol.
So basically, we took data points of how long it took to dissolve the potassium hydroxide into the methanol, and then applied a fourth polynomial degree curve fit because it fit it pretty well. And this is the equation for dissolve time that we came up with. This R right here is the ratio added by volume of potassium hydroxide to methanol. All right. Now, this dissolve time is just a rough estimate of how long it would take per ratio volume to dissolve into the methanol. We then decided we were going to try and figure out if we could predict the mixing temperature of like what the max temperature is per how much volume potassium hydroxide we add. Now, the only issue with this is that we waited until everything was dissolved before we took the measurements of the temperatures. Thus, time kind of became, we didn't incorporate time into this, so that's kind of a big deal. But anyway, we figured that in a larger scale test, this is the process by which we would go about creating a relationship to determine how much the temperature would rise per ratio of methanol or potassium hydroxide added to methanol. And the main idea for that is if we took the derivative of that relationship, we could be able to determine how much temperature rise there would be per ratio added, like the temperature gradient. So, and that's crucial because when you mix methoxide, one of the biggest issues is causing a potentially dangerous exothermic reaction. So we want to make sure that we keep the temperature under control, at least as much as we can. So, and now I'll hand it back to Gabriel Kowski to talk about our static mixing components.
Back up here for a second time. So again, Dave Bukowski, I'm going to talk to you now about the static mixing component of our reactor. And before I do that, I have a little bit of a show and tell here. And then pass this around. This is the static mixer, at least one section of it that is used in the apparatus of the project, just so for your reference. So I'm going to talk about, first of all, the geometry. So when we talk about mixing, there's a lot of ways you can mix stuff together. You can have an impeller attached to a motor, which mixes fluids together. Another perhaps impractical way to mix would be having a really, really long tube. Just mix fluids together that way. Probably not the best way to go about doing something. Third way, and the way that we used here, was using a static mixer. A static mixer uses simple geometry. It's pretty much just a tube filled with elements that they don't move, and you move fluid through the mixer, which ultimately causes mixing, and I will describe that in just a few minutes. There are helical elements inside the static mixer. These helical elements are short sections, approximately twisted about 180 degrees, that are used to actually mix the fluid together, whether it's two fluids or multiple fluids besides that. they are placed in series with one another as you go from the beginning of the static mixer to the end of the static mixer. And the trailing edge of one element and the leading edge of another element are placed at a 90-degree angle to one another. This helps with the mixing process altogether.